Elon Musk's Physics Task Force, Part 1. Predicament statement. SpaceX is launching a rocket off of the edge of a cliff. The rocket produces a constant thrust force whose magnitude is unknown. The rocket is directed at an angle above the horizontal. The rocket crashes into the ground unknown distance from the base of the cliff at a velocity that is unknown. Our knowns are the angle, the mass, the cliff height, and the distance away from the start. Our unknown is the magnitude of thrust speed at crashing point, the final velocity in the y direction, and the final velocity in the x direction. How are we to look at the problem? We need to first envision the situation, make assumptions, model the situation, then tackle the problem, state our case, find the magnitude of the thrust force, solve for final velocity, then finally create a position versus time graph.
We envision the situation by stating our known variables that are the mass of the rocket, the angle in which it's launched, the cliff height, and the distance from the start that the rocket lands. We don't know the magnitude of the thrust force or the final velocity. We can find these unknowns by using the following equations. The net force equals the sum of all forces acting on an object. Newton's second law equation that states that the net force equals mass times acceleration. Velocity kinematic equation that's final velocity equals initial velocity plus acceleration times time. The position kinematic equation that's the change in x equals initial velocity times time plus 1/2 acceleration times time squared, and trigonometry. We assumed that there was no drag force, also known as air resistance, but we determined that there was thrust force and gravity acting on the rocket. In our model of our situation, we depict a rocket launching at angle theta off of a cliff of height h and landing distance d away from the base of the cliff. From this, we can understand how the trajectory affects the situation, envision the forces acting on the situation, and use it to help us make a free body diagram.
This graph simply describes the path that the rocket travels after crashing into the ground d distance away. It's a parabolic shape because the rocket launched upwards with some unknown thrust force at an angle before a malfunction caused it to crash into Earth. By using Newton's second law and two kinematic equations, the final velocity can be solved for. In the first step, we broke up the forces into their x and y components and then added up all the forces to get the net force. Next, since we had a net force, we could solve for the acceleration in the x and y components. Once this was done, we plugged in the equations denoted for acceleration to find the final velocity in the x and y components. To get the final velocity as one value and not broken into any components, we took the magnitude. Our last step was to get all the variables in the equation into known values, which meant solving for the time that the rocket was in flight in terms of d and acceleration. This was the last step, and from looking at the final equation, you can see our result. By running a quick unit analysis, we could ensure we got reasonable units for velocity. To do this, we assumed all distance variables were in units of meters, all time variables were in units of seconds, and all mass variables were in units of kilograms. From following the steps on the screen, you can then see that indeed units cancel out and yield a result of meters per second, which makes sense for a velocity value.
Now on to slide number 10. Here we are going to use the sense-making strategy of special cases. We used F sub t instead of the long definition for thrust for the ease of reading. We decided to launch a rocket straight up some distance. We expected the rocket to not have, or to have a vertical component and no angles. If we look at the math, we see that there's no horizontal component or trigonometry involved. This allows us to break down the kinematic equations into chunks that we can understand and substitute where necessary. If you remember the equation that we solved for correctly, you'll notice that this equation that we solved for here is actually a chunk of what we solved for previously. And if you observe the variables, you notice they cancel out to units of distance over time. Moving on to slide number 11, I felt that it was interesting that I could assume there was no drag. I definitely think it would have been more challenging if there was. Kanan felt as though the angle thrown into the problem made it challenging, but other classwork prepared us for it. Emma felt as though addressing the problem in 2D was definitely challenging compared to some other coursework, and Ramsey found the mixture of projectile motion and force to be challenging, and a challenging new experience. All in all, some of us found it to be not too different from previous problems, and some of us found it to be pretty different. Moving on to slide 12, you'll notice our citations. Thank you for coming along with us on this physics adventure, and we hope you enjoyed.